So let's get started. So of course, slope y-intercept form, you've probably seen this in your classwork, y equals mx plus b. And I like to say that in math, you know, we're not super creative with how we name things. This is called slope y-intercept form because it gives you the slope and it gives you the y-intercept. I know, very creative, right? When we graph something like this, let's just talk about what are intercepts. Well, if it crossed the x-axis, it'd be an x-intercept. The y-intercept is where the graph crosses the y-axis. And a lot of your work, especially in math 9 and 10, this will be something that we view as kind of where the graph starts. That's kind of one way to look at it. I mean, of course, we have negative x and y. The graph could continue, but with a lot of our word problems in real life situations, this is referencing where the graph would start. We'll get into word problems in a little bit later, but this would be like what we call a startup cost or a constant of some variety. And that's why in this equation, the slope is attached to x. It's a rate of change. As x changes, the value of y will change, but b is just a number. It's a number we're going to add to whatever this value is every single time. So let's keep going with some examples. The question says, graph this function. And we know it's a linear function because it's a straight line, which means if we can find either 2 points or if we have 1 point in the slope, we can graph the line, right? So think about how that looks. So here's y, here's x. If I had 2 points, I can connect them, I know the function. Or if I had 1 point and then I knew how much it changed to get to the next point, I could create that function, right? So for example, let's say the function is y equals 2x plus 3. And we want to graph this function. So we're going to start with our Cartesian coordinates, we call this, right? And again, we know that this is the slope. And we know this is the y-intercept. Which means it's going to intercept y at 3. So if we had like 1, 2, 3, 4, 5, for example, it's going to start at 3. And if we had 1, 2, 3, 4, and x, 2x, remember we're going to talk first about slope being rise over run equals slope, okay? So if I have 2x, that means my slope is 2 over 1, because we know any number can be written over 1, right? Which means the rise is my 2, and the run is my 1, which means this point, think about where we started. The first point was 0, 3. That's our y-intercept. So if I started at 0, my run means I'm going to go over 1. So I move over 1. And my rise says I'm going to go up 2. 1, 2. That's my next point. If I wanted to continue, I can make my graph a little bit bigger. I'm going to go over 1. That's my run. My rise is still 2. So I'm going to go up 1, 2. That's my next point. And I can go ahead and I can draw a line through my points. It should be a straight line. And our points, right, would be 1, 5, 2, 7. Another thing we could do is we could make a table of values. So I'd say, well, when x was 0, y was 3. Then I'd say, well, when x was 1, y was 5, 2, 7. And we notice this is going up by 2 every time in the y. As long as x goes up by a constant, you know, it's not like jumping by like counting by 2s or something. This change in y relates to my slope. We see it's going up by 2. So each number should be adding 2 in the y direction. But it started at 3 because that was this guy. So that's another way we can express the relation y equals mx plus b through a table of values and a graph. They're both going to demonstrate the same relation. How you go from point to point depends on the slope. Where the graph begins depends on the y-intercept. Let's talk a little bit more about slope, and from there we'll introduce slope point form as another form of a graph. So slope, we have y equals mx plus b. Slope is the m in this guy. We've also said it's the rise over run, which is most useful to us when we're graphing, when we have an actual graph we can look at. It's also equal to the change in y over change in x. That's another way that we can refer to slope as a rate of change. A rate of change we know means like think of the words rate and change. So rate has to do with like how quickly or slowly something happens, and it's a rate of change. So we're talking about how quickly or slowly y and x change. That's slope as a rate of change. Finding the change in y requires having 2 points, and finding the change in x requires having 2 points. So now, for example, we'd say, example. So we just said rise over run is the easiest way for us to interpret slope when we're graphing. But what if they already gave you the graph? What if they gave you something like this, and we had a series of points? We had 0, 2, and maybe we have like 3, 5. And we want to know what is the function in y equals mx plus b. What is this function if I wrote it as y equals mx plus b? Well, we're going to confirm with our rise over run. So we could say, well, you know, how did we go from here to here? Well, the run was 3 and the rise was 3 because I went from 2 to 5. So my slope would equal rise over run, which would equal 3 over 3, which would just reduce to 1. The slope is 1, right? But let's use this one to prove that as well. Let's say we didn't have the graph and we just had 2 points, and it's kind of harder to keep track of it maybe. This is another powerful way for us to calculate a rate of change. This point comes second, and sometimes we wonder, well, wait, how do we know if it's x or y? Because, you know, what if our graph looked like that and I had these 2 points? You know, now the y1 is like taller, right? Like which point do I pick first? Do I pick the higher point? Do I pick the furthest point? My answer is, think about how time moves. Time moves forward, which means this point happens first. This point happens second if we were traveling through time, forward through time. So thinking about it that way, well, that means that, we'll use another color here. If this is our first point, this becomes x1, y1. This becomes x2, y2, because we know that every point is an xy coordinate, right? So that's why if this is 0 for x, 2 for y, this one was 3 for x, 5 for y, sorry. Those are my x and y coordinates. This point comes first, so in my formula it'll be x1, y1. 3, 5 will be x2, y2. So we can go down to our formula and we can say, well, we have y2 minus y1 over x2 minus x1. So that now I take these numbers, 5 minus 2 over 3 minus 0 equals 3 over 3, which equals 1. Our slope is still 1. Then again, the question says, what's the function? Y equals mx plus b. Well, I have y equals, slope is 1, so 1x plus b. What's b? Where did the graph start? Right here, 0, 2. X being 0 will always correlate to my y-intercept. So plus 2, and that's my function. There's different ways we can display a graph. So one of these is slope y-intercept form. It's the one we've been talking about, slope y-intercept form, and it's y equals mx plus b. Another way is called general form, and it looks like this. It looks like ax plus by plus c equals 0. We're not going to go into that today. This one is the most useful to us because it tells you the slope and the y-intercept. It tells you 2 characteristics of the graph. This doesn't do that for us. When we have general form, usually we want to rearrange it into slope y-intercept form. We can talk about that, but we're probably not going to talk about it today. Another one that is actually useful is what we call slope point form. Now again, what do we know about math? Well, this is called slope y-intercept form because it had the slope and the y-intercept right in the name. Slope point form probably has the slope and another point. Let's talk about how we get to it. Remember this, slope. Slope is equal to y2 minus y1 over x2 minus x1. If we put these guys in brackets, and what if I rearrange? What if I multiply both sides by x2 minus x1? Okay, x2 minus x1. So now I have m x2 minus x1 equals y2 minus y1, just like that. This is called slope point form. We have the slope, and the way we would display it, maybe we'd write it like this. X minus, we would take a point from the graph. Just like this one gives you the slope and the y-intercept, this one would give you a point. So let's pretend this is the point, okay? Then when we're asked to find the slope, okay? So for example, this is an equation in slope point form. And so the point that we have is 2, 3. Okay, 2, 3. And we're asked to find the slope. And maybe we have some other points. Maybe we have 1, 4, and maybe we have 3, 2 as other points on our graph, right? We don't have this y-intercept this time. And for the sake of the example, we're not going to find it. Let's pretend we don't have the y-intercept. We don't know how to find it. We can find the slope. Again, we'll just go with the rise over run. We could do our change also, but let's go with the rise over run. Our slope, we are going over 1. We're going down 1. So our slope would be rise over run, and it'll equal -1 over 1, which is reducing to -1. So the slope is negative because it's going down. If our line goes down, it has a negative slope. That will always be true. But we could also find the slope using this new formula. We could take one of these other points and plug it in. And again, the 2 and 3 are given as part of the point. Just like this formula here, the slope y-intercept form would have given you the b value, the y-intercept, and the slope. This one gives you a point and the slope. If we're asked to find the slope, all we have to do is take another point from the graph. So I'm going to take 1 and 4. I would have m, and then where x is, I'll put my 1 minus 2 equals 4 minus 3. Now I can rearrange to solve for m. So m times 1 minus 2 is -1 equals 4 minus 3 is 1. Divide by -1. I find m equals -1 once again. So I would put this into my formula, but this graph described as slope point form could be expressed as this. That would be slope point form. But again, I could pick any point and put in my equation. So it could also be expressed as x minus 1, y minus 4. Or it could be expressed as x minus 3, y minus 2. These would all graph the same line. If we had a graphing calculator out, or we wanted to graph them, something like that, these would all graph to the same line. Let's do a proof of that now. We're going to convert from slope point form. So this is slope point form. X minus, I'm going to write a and b, just to remind us that would be a point that we would have values for. And just like how b would be a point in that other formula. So those are our formulas, those are the ways we're going to express linear equations. Now let's talk about these guys some more specifically. Let's prove that all of these 3 versions of slope point form describe this same line, okay? Here's how we're going to prove it. We're going to convert from slope point form to y-intercept form. All right? Let's start with the first one. -1, x minus 2 equals y minus 3. We're going to start with our distributive property. The -1, our slope, has to go into both of these. So it's -x plus 2 equals y minus 3. There's nothing to multiply to y, so my brackets just vanish. If this is super unclear to you right now, don't worry. We're going to make another short in a little bit about the distributive property, so you'll be able to see that on my channel as well. We'll cover the distributive property and we'll cover factoring. But for now, we're multiplying the -1 in using the distributive property. All right, Now we want to isolate y, because remember our target is this formula, y equals mx plus b. So I want to isolate y. Well, what if I add 3 to both sides? So now I have negative x plus 2 plus 3 equals y. I'm going to just write it in a different order and combine my like terms. So this turns into y equals negative x plus 5. So that would be, and our slope is negative 1, right? So this is negative 1x, we know. So that would be slope y-intercept form of this first equation from slope point form. Doesn't prove they're the same until I figure out all of them. Let's look at negative 1, x minus 1 equals y minus 4. Distribute this in, negative x plus 1 equals y minus 4. Add 4 to both sides. So I get y equals negative x plus 5. 1 plus 4 is 5. And let's check the last one. Negative 1 x minus 3 equals y minus 2. Distribute my negative 1 in. Negative x plus 3 equals y minus 2. Add 2 to both sides. I get y equals 3 plus 2 again is 5, negative x plus 5. So we can see all of them relate to the same equation in slope y-intercept form. So as we can see, each of those three equations in slope point form do relate to the same equation in slope y-intercept form. That is, they describe the same line. They describe the same line. And you might ask, well, why is that? Why does it work out this way that they all have the same equation in this form when they all had different equations in this form? Well, the reason for that is they're points on the same line. Remember, slope y-intercept form shows you the slope and the y-intercept. The y-intercept is 1 point. That never changes. Slope point form shows you the slope and a point, A, B, being x, y of some point on this line. If I choose this point or this point, my equations will look different. But because the point is different. But what's not different is the change. What's not different is how we go from x to x, from y to y. 1 to 2 is still a change in 1. 2 to 3 is still a change in 1. 4 to 3, 3 to 2, those are still both negative 1 changes. Meaning, all the points that belong to this line are related to the same rate of change. And so if it's the same rate of change to go between points, then it doesn't matter which point I choose and put into the equation for slope point form, because x and y are related to each other in the same way that 1 and 4 are related, 2 and 3 are related, 3 and 2 are related. They're related to each other in the same way they're related through this slope. So that's why it'll work out. Whether or not I chose this point, or this point in my equation, they will all return the same result in the form y equals mx plus b. And they will always do that because they belong to the same line. We're just choosing different points when we use this one. Whereas in y equals mx plus b, there's only 1 point, the y-intercept. So hopefully that makes sense. Let's continue here. We're going to do one more quick example, just describing a graph of a linear function. So we've talked about the y-intercept already. It's where the graph crosses the y-axis. The x-intercept is where the graph crosses the x-axis. Make my points bigger. So let's pretend this is 5 and this is 3. X is 0, y is 5. That's my y-intercept. X is 3, y is 0. That's my x-intercept. And the slope I can calculate any number of ways. Let's try our y2 minus y1 over x2 minus x1 again to find our slope. This point came second. This point came before it, again in our flow of time, as we say, our flow of time. So this makes this y-coordinate y2 and this one y1. This coordinate x2, this coordinate x1. 0 minus 5 is negative 5, 3 minus 0 is 3. So my slope is negative 5 over 3, and I could do couple of formulas. I could do y equals mx plus b, where y equals negative 5/3 x plus 5. The y coordinate of this point is my y-intercept. Or I could do my slope point form that we just discussed. My slope point form, which looks like this. And I could say that's negative 5/3 x. I could choose either point. Let's choose the x-intercept, because why not? So x minus 3 equals y minus 0, or just y. So that would also be slope point form. I think typically we don't like to use the intercepts in slope point form because these guys go to 0 and we usually want to keep a different point, but it's still the right form. It would just be if you looked at it on your tests, for example, if you saw an example like this, it might be kind of harder to recognize it's in slope point form when there's a 0 because they might not write it. You might see y equals this stuff and wonder kind of what it is. So, but it's still the right formula. If we threw, and it's negative because our line's going down. If we threw another line on our graph, maybe this one, and let's say that this is 2, let's say this is negative 4, and now this is my other line. All right, so let's do this point, negative 4, 0, y is 0, would be my x-intercept. And this point, x is 0, y is 2, would be my y-intercept. So in the form y equals mx plus b, again, I want to find the slope. Maybe this time let's do a rise over run. So how do I go from here? Negative 4, so I go negative 3, negative 2, negative 1, 0. So I moved 4 over, and then I go from 0 and I go up 1, 2. I moved up 2, so my rise over run becomes 2 over 4, which will reduce to 1/2, and it's positive because my line is going up. It's positive, so that makes sense. So I could have 1 over 2x plus 2, the y coordinate of my y-intercept. Or again, I could say, let's do slope point form. Slope point form would be 1/2 is my slope, x minus, let's use the x-intercept as our point again. X minus negative 4, x minus negative 4 turns into x plus 4, and it equals y minus, well, y is 0 at that point, so y minus 0 would be a slope point form example. So there's 2 examples of how to describe a line in either slope y-intercept form or slope point form. What we're going to talk about next is where these intersect. We're going to talk about if it's a perpendicular intersection where they make a 90 degree. And we're also in that conversation going to talk about parallel lines that never intersect. We're going to talk about that in our next video, so stay tuned for that. And like I said, if anything else, any of the earlier topics, if they don't make sense, send me an email. It's linked in my channel, and we'll make a video going through that. Probably our distributive property and our factoring will be next. I know those are some things that a lot of people have been wanting some help with, so we'll make something about that. But hopefully this here gives you a hand with understanding linear functions, how to graph them, and how to find the slope. And the slope, again, that's a big one. All of these ways are ways to find the slope. So if you see m in any of your formulas and you have to find it, or if they ask you to find the slope in any of your formulas or in a word problem or something like that, we'll talk about in the next one as well what that represents, what slope could represent in the context of a real world problem. You can find the change in x over the change in y over the change in x, the rise over run. You can find that on your graph if it's there, or you can take 2 points and use subtraction to find how y and x change in relation to each other. All of these methods will still relate to m in your equations, and they'll all give you the slope of that linear function. Startup cost in a lot of problems about money. We're going to talk about those guys in our next video.